Hello everyone, welcome to the 3.6 notes. If you didn't notice, we're skipping over a couple. I think the last notes we actually did were 3.2. We've kind of been doing 3.5 the whole time, so we're not really going to do specific notes, but we are skipping over some things. The reason for that is I would just rather do a couple things really well than try to spread you guys a little too wide. But if you guys want to get some of those numbers in between that you're missing, feel free to go on Khan Academy and try to learn 3.3 and 3.4. But today what we're going to do is higher order derivatives. And so this is just adding one more skill onto what we already know how to do. So first, you guys are probably going to recognize what's in the blue square. It says if y equals f of x, the first derivative of f of x is, and so these are different notations you use to represent the first derivative. You could use y prime, f prime of x, dy dx, and then this is the one that I've been trying to help you guys more with recently is you do the derivative of f of x with respect to x. So you say it like the derivative of the part that's in the parentheses with respect to x. Now, though, let's say that y equals f of x, and we want to find the second derivative, which, what is the second derivative? It is essentially just two derivatives. So you take the derivative, and then you take it again. So the way that you would talk about it if you were using the y prime notation is the second derivative would be y double prime. Then it would be f double prime of x. Then it would be d2y dx squared. I don't really know exactly why they put it like that, but they do. So, and then this would be hold on, I'm cheating a little bit. Okay, d2 f of x all over dx. And so those would be what the second derivative looks like. So some of you might be wondering, why would we find the second derivative? Well, this is something we're going to do a lot in Unit 4 and in Unit 5 and 6. But for example, the derivative of the derivative of a position graph is velocity. Well, what if you wanted to go from position to acceleration? Well, because the derivative of velocity is acceleration, then the double derivative of position is acceleration. And so basically every time you take a derivative, and this is what we're going to learn more about next unit, is you're taking a rate. And so say I'm trying to do something besides walking. Say I'm like filling up a bathtub. And so on my x-axis, I have time, and on my y-axis, I have how much water is coming into my bathtub like per second. If I would take the derivative of that, I would find the rate of change of the water in the tub. If I take the double derivative, I find the rate of change of the rate of change. And so again, that's a lot of what we're doing in Unit 4, but that is why we need second derivatives and third derivatives, is because they tell us a lot about real-world situations. So this pattern continues if you use third derivatives or like nth derivatives. So like say you do the fourth, the fifth derivative. We are like not really ever going to take more than third derivatives because again, like the big connection is that it's like position, velocity, acceleration. So most of the time we're working with this, we're taking second derivatives, but the pattern would just continue. So I know that I just said that, but we're going to go ahead and we're going to find the third derivative just for fun. So first, we have the original function. If we want to find the third derivative, we have to start by finding the first derivative. And so you just take the derivative of everything. This would be 8x cubed. That term, the derivative of negative 5x is negative 5. And then the derivative of sine x is cosine of x. And so that's the first derivative. Now we go to find the second derivative. And all I have to do to find the second derivative is look at the first derivative and take the derivative of that. So this will be 24x squared. The derivative of 5 is 0, so I'm not even going to write that down. And then the derivative of cosine is negative sine x. So I found the second derivative. So you've already learned your big new skill. Go one more time, and I'm going to take the third derivative. And to find the third derivative, I just take the derivative of the second derivative, and I'll get 48x minus the derivative of sine x is cosine x. And it's minus because that minus sign carries down. And so that is our answer. So not too bad. Let's go on to our next one. Feel free to try this one on your own. You are going to have to remember what the derivative of secant of x is. So keep that in mind. This one's a little bit trickier than the last ones. But let's go ahead and find it. I'm going to use, because it's y, I'm going to use the y prime language. So I'm going to write y prime equals, okay, the derivative of secant is 2, and this is going to be a little tricky, but it's 2 secant x tangent x. And it's not tricky yet. You'll see why that's tricky. And then e to the x is like the least problematic derivative of all time. It's plus e to the x. So I want you to try to take a guess without me telling you, why did I think that this became more tricky? Think about it in your head in a second. Okay. maybe you got it, but the reason this becomes more tricky is that secant of x and tangent of x are connected by multiplication. And so now, if we want to find the second derivative, I have to use the product rule because I have a product here. I'm doing 2 secant of x times tangent of x. And so I have to use my product rule. And it looks a little confusing, but it'll be okay. E to the x still, it's great over there. So the derivative of the first function is 2 secant of x times tangent of x. And then you always multiply by the original second function, which was tangent of x. And then now I have to do the other part of the derivative, or the product rule, sorry. So that'll be the original first function times the derivative of tangent x, which is secant squared x. And so this part right here all connects to this. So this whole section is just the derivative of the first term, which was 2 secant x tangent x. But then we can just take the derivative of e to the x, and that part's great. You could leave your answer like this, but I am going to simplify it because if you look over here at the first term, there's 2 tangents. So I can turn that into tangent squared x because there's 2 of them. So I'm going to make that like this. And then over here, there's actually 3 secants because there's 1 secant right here and there's 2 right here. So I'm going to make that plus 2 secant cubed x plus e to the x. A really fun fact is we're not going to do this, but Pythagorean identities would simplify this down really, really well. But for the sake of time, we'll just move on. But if you want to know what I mean by that, you could like simplify this and reduce that a lot. But this is going to be our answer. 2 more problems. So these problems are really exciting and fun, but like really, if you thought implicit differentiation was hard before, this is like implicit differentiation on steroids. And so really just brace with me. I gave you guys 2 pages on your notes, so you have a little bit more space for these. I'm going to see if I can add. Let's just copy. I just want to add a little bit more space. I don't think that worked. You have to paste. Okay, well, I'm going to try to make room. Sorry. Okay, so use implicit differentiation to find the second derivative. So anytime we want to find the second derivative, we have to start by finding the first derivative. And we have to use implicit differentiation here because y is not solved for. So I'm just going to go ahead and take the derivative of both sides with respect to x. And on the left side, the derivative of y squared with respect to x is 2y times dy dx. On the right side, the derivative of 7y with respect to x is 7 dy dx. And then plus the derivative of 4x with respect to x is 4. So now the next goal would be to get the dy dx's on the same side. So I'm not even like really thinking about the fact that I have to find the second derivative. There's no need to think about that yet. So these cancel out, and I'll have 2y dy dx minus 7 dy dx equaling 4. I got to get the dy dx's like by themselves. So if I look there, both of those terms have a dy dx. So I'm going to factor those out. I'll get 2y minus 7 equals 4. And then I will divide 2y minus 7 on both sides. So dy dx is completely by itself. Slow down if you need to kind of think through that again. Okay, I'm not gonna square it because that's not our answer, but I am gonna highlight it because it's important. So that is, that is our first derivative. And so to get the second derivative, we have to go from our first derivative. So same thing, I'm gonna start by taking the derivative on both sides because what's on the right side just represents the derivative of y with respect to x. So I'm just going to take the derivative on both sides. Taking the derivative like of a derivative, that just makes that like notation. I'm going to turn it into dt d2y dx squared. And then on the left side, before I take the derivative of that, I'm going to rewrite it so that I can use the chain rule so I don't have to use the product rule. So I'm going to rewrite it like this real quick. If you want it, sorry, I didn't mean to say the chain rule. Wait, yeah, it is a quotient. I'm going to rewrite it so I don't have to use the quotient rule. And now I just need to take the derivative of the right side as well. So I'm taking the derivative of the outside part. So that will become -4. I have to use a chain rule here because it's a composite function. This will be 2y minus 7 to the -2 power. And then I have to take, because it's a chain rule, I have to take the derivative of the inside. When I do that, the derivative of 2y minus 7 with respect to x is 2 times dy dx. Sorry. See if you can understand like what happened right there. Just take a second to process that. Okay, so I'm gonna simplify this a little bit. Sorry, I'm having a coughing attack, as you can tell. This -4 and this 2 becomes a -8. This can move back to the denominator. So embarrassing. Okay, times dy dx. Okay, we're almost done. However, we don't really know exactly what the second derivative is because of this section right here. But remember, we know what dy dx is. Dy dx is this. It's 4 divided by 2y minus 7. So my last step to actually find out what this is, because I want the answer to be like all in terms of, I want it to be all in terms of like x's and y's, is I'm just going to plug in that expression for dy dx, because that's what we figured out what the first derivative was. And then if I mean, that's technically the correct answer. You don't have to simplify it, but we should learn I'm just multiplying across. -8 times 4 is -32. And then 2y minus 7 squared times 2y minus 7 is 2y minus 7 cubed. And that is your answer. Okay, we're going to go on to the next one. The next one's pretty hard, but you guys got it. Okay, it's the same idea. We want the second derivative. We actually want the second derivative at a point this time, too, which actually makes our problem a little bit easier. But I'm going to go ahead, and to do this, I have to find the first derivative. So I'm going to take the derivative of both sides. That will equal 2x plus 2y times dy dx, which equals 0. And now I just have to get dy dx by itself. So, okay, I've had to stop and pause this video like 3 times because I keep coughing. But we're back, and I'm going to try to make it through the rest of this problem. But that's the derivative, the first derivative, dy dx. It's -xy. And so now what we're going to do is we're going to go ahead and find the second derivative using the first derivative. So, oh, sorry, hold on. So you're going to take the derivative of both sides of the new derivative with respect to x. And on the left, that's going to become d2y dx squared, which just means the second derivative. And then on the right, we're going to have to use, what do we notice? It's a quotient, and y is not soft warp, right? It's a quotient, though. That's a big idea. So I'm going to have to use the quotient rule. So the derivative of x with respect to x is -1, so it'll be -1 y minus -x. The derivative of y is dy dx, and then all over y squared. Now, this is something that you guys can go ahead and do at this point, because you can't always do this, right? Like in the last problem, we had to plug in dy, like we would have plugged in -x divided by y in here. But the difference between this problem and the last one is that we have a specific place that we want to find the second derivative, and that's 4, 3. So what I can do is I can go through this, and I can just go ahead and replace all of these values with either 4 or 3. So, for example, like 4 is our x value, 3 is our y value. So I'm going to replace this with 3. And then I'm going to replace this -x with a -4. We know that dy dx is -xy. And so if I use that point, that's essentially -4/3. So I'm just going to replace -4/3 here. And then this is all going to be over 3 squared. So these problems are actually a lot easier if you have a point to plug them in, because you don't have to do as much algebra. You can just like plug in numbers at some point. So now I'm just going to simplify, and I'll get -3 minus 16/3 all over 9 I guess we can simplify that down. That would be like negative 9/3 minus 16/3, which equals negative 25/3 over 9, which equals keep, change, flip, equals negative 25 over 27. But honestly, you could have left it here. You honestly could have left it here. You could have left it here. But that should be your answer. If I have any computation mistakes here and you think you see it, send me an email. I'll give you an extra credit point. I don't know. I totally could. I'm just saying that because there's a lot of algebra here. And so if I mess something up, send me an email. Whoever gets it first would get an extra credit point. Hopefully I don't have anything wrong. That's it. Have a good day. Bye.